Okay, so going to carry on with current of electricity. So here's an example that's in your notes. So we've got here a 230 volt motor is connected to a main supply. Find the work done when 8 coulombs of charge flows through the motor when lifting a brick to height h. So what's actually happening here? You've got to think about we're lifting something up to a certain height. Okay, when it talks about some sort of height h, there is a certain amount of work done on the block to raise it up to gain gravitational potential energy. So we're just trying to find work equals, and we've got a voltage there and we've got a charge, so it must just be VQ. So carry on from there. This one here is now only 40% efficient. So it lifted the 10 Newton brick to a height h. Calculate this height. Okay, so if it's only 40% efficient, then we're actually wasting 60% of its energy. So let's say we got the answer from the start there. That is assumed that height h there that it gets to in the first one will be assuming 100% efficiency. Okay, but in fact, it is not 100% efficient, it's only 40% efficient. So 40% of that work done will be able to raise that thing up to that height h. Okay, so that's a bit of a clue for that question. Okay, EMF stands for electromotive force. E.M.F. Okay. What is it? Well, essentially it's the same as potential difference, okay, except for potential difference, which is normally, we defined it as energy that was converted from electrical to some other form, so let's say heat or something like that. Okay, EMF is some other form of energy into electrical. So if I was going to define it, I would look at defining it as energy provided between electrical energy provided between 2 points in a circuit, as opposed to potential difference, which is in electrical energy converted to another form between 2 points in a circuit. Symbol V, unit V formula, same as your potential difference. Okay, so here we've got resistance, which is quite tricky. Okay, but essentially resistance is an impediment to the flow of current. Okay, so let's imagine we had sort of a slide, and at the top of the slide we had a ball. Now the voltage can be associated with the height. Okay, if you increase the voltage, you'll increase the flow, which is the current. Okay, the other thing you could change though is you could change the slope size. Okay, now that could actually effectively be the resistance. Okay, the greater the slope, the greater the current. Okay, whereas the size of the slope here, so let's say this one here, this one would be a resistance of 10. This one here would be a resistance of 1. Okay, so the current is inversely proportional to the resistance. Okay, so if you increase resistance, you decrease the current. If you increase the voltage, you increase the current, so that is directly proportional. Defining formula for resistance is one you've seen before. Okay, but usually you've seen it as V equals IR. It's actually the defining formula for resistance. What's the unit? It's the ohm. Now if you think about this formula here, that if you had a resistance value of 10, you could have a voltage of 10, current of 1. But the ratio is always going to stay the same. So you could also have 100 volts, and that would create a current of 10 because of the ratio. Okay, so resistance is about how the push to current ratio is affected in a circuit. So in class we're going to do some IV characteristics of three things. We're going to do a resistor, we're going to do a lamp, and we're going to do a diode. How do they should really look like? Okay, so the first one, let's do a resistor. Okay, so doing a resistor, you have some axes. We're going to do IV, so we're going to do I on the Y, V on the X, and we'll just put a line in. The line is going to be nice and straight. However, if we're going to do we're going to do something else, this time let's look at doing the lamp on the same axis. Draw the resistor one back. Oh, actually I'll make the resistor one yellow. Resistor's nice and straight. The lamp. Now, a lamp is actually going to be a curve. Okay, it's going to be a curve like that. Okay, and for the other way, it's going to be a similar way. Remember, this is just a negative voltage. This is just turning the connections around. So positive in the battery will be negative. Okay. Now, so you can see we've got a curve there for a lamp. What does it tell us? Well, we actually find resistance by finding points. Okay. Now, if you look at the ratio of these things, the ratio at this point here is actually going to be lower than the ratio at that point there of V over I. So we've got a larger V for not much higher I, okay, compared to here where there's a smaller V for a very similar I. So this one here will have the largest, this one here we have the largest V divided by I ratio. In other words, resistance is increasing. And the last one you'll draw will be the diode. Now that one there will go along for 0 for a bit and then suddenly increase. Okay, and usually that's around about 0.7 volts depending on the diode. The other way though, when you connect the cell around the other way, it will actually go along at 0. Okay. And there may be something that's sometimes called a breakdown voltage. In other words, you overcome the resistance and it just suddenly breaks down. So what a diode does, it really only allows current to flow in one direction only. Now, so important note I just said before, resistance is not found by finding the gradient of the graph. So if I had a graph, okay, we had a nice little curve, you don't find, do not at any time, for that point there, find the tangent, okay? We don't do that. What you do is you just take the V value and the I value and just do V divided by I at that point. Now Ohm's law, if you look in the dictionary, is essentially talking about how the ratio between V and I, between potential difference and the current, will stay constant provided the temp is constant. Okay, that's that important point there. Okay, a couple of other things affect the size of a resistor. We looked at how it changes the voltage and current, but resistance will also, how do you actually get resistance in the first place? Well, you just get a tube of wire, okay, and so the wire here will have a cross-sectional area and it will have some sort of length to it. Okay, now there's two things that can affect it, okay, according to what I just did there. There's the length and the area. The greater the area, the easier it is for current to get through. Okay, so if you increase area, you increase the current. Okay, so in other words, you must decrease the resistance. Okay, so resistance is inversely proportional to area. Increase area, decrease resistance. Length of material, you make a wire longer, you decrease the current, so you must be increasing the resistance. So longer wire means you have, longer the wire, the greater the resistance. And the type of the material, which is something called resistivity, is a value that's dependent on the material. Okay, so copper and gold are two different metals and they have two different resistivities. In other words, one will conduct better than the other one. So material itself has constant proportionality, which is called the resistivity. Similar unit for resistivity. Okay, the symbol is rho. Okay, unit. Well, you can use the formula. Okay, which we'll look at in a second. Actually, we'll look at it here. So usually, how we'll remember this formula will be we'll look at resistance. So resistance equals rho L over A. Okay, to find the unit, just put in rho equals, and then you just rearrange. Okay, RA over L, and then you just simplify that. So an example, a conductor has a length of 10 kilometers and a resistance of that, cross section of that was resistivity of the conductor. Okay, so rho equals RA over L, and you just put the values in. Okay, remembering that the length is 10,000, and well, that should be a square. The cross-section area is 0.25 millimeters squared. Okay, remember how big does a millimeter compare to a meter? We need to make this into meters squared. Okay, and it's not just 1,000 difference. Okay, there's actually going to be 1,000 difference on each side of a square. Okay, so it's actually 1,000,000 difference. If the wire in example 1 is a length halved and diameter quarter, was the new resistance of the wire? So if we look at the resistance formula, rho L over A, that is staying the same. Okay, but we are halving the length and the diameter is quartered. Now remember, area is pi r squared. So if we quarter the diameter, which is effectively the same as quartering the radius, then squaring that, we're going to have a big change. So what you've got to think about is, what is a quarter squared? Well, it's going to be 1/16, isn't it? So the area has actually gone down by a 1/16. Okay, and then you sort of just combine those two values to see how much that resistance has changed by.